And hello everyone, welcome back once again to the online lectures of design of sheet structures. And in today's session we are going to discuss about determination of collapse load. So in the last session I have discussed about what is mechanism and what is collapse load, okay, and how the mechanism will occur. So what is mechanism? What is mechanism? So I will just recall, when any body subjected to external load or any member subjected to external load, it will offer the resistance, but at some level of load, or the specific level of load, body will stop offering resistance to external load. For example, this go and increasing load, so body is offering resistance now, okay, but at some level of load body will stop offering resistance to external load and the structure will convert into mechanism. Okay, so what is that? When the body stops offering resistance to external load, that is called as mechanism. And still the load increased over the member beyond a specific level of load, the structure will collapse, and that load is called as collapse load. And today's session we are going to discuss about how to determine that collapse load or determination of collapse load, because determination of collapse load is important, because ultimately when you find how to get the collapse load, so we can restrict the load over the member. You are getting my point. Once if you know how to calculate the collapse load over the member, we can very easily find out. Once if you find out the collapse load acting on the member, so we can restrict the load over the member. So we should not allow the load to reach the collapse load. Once the collapse load, if reach collapse load, the collapse will occur in the structure. So we should avoid to reach our load up to collapse load. So that is the reason we are going to discuss about the determination of collapse load. Okay. So there are two methods basically for the calculation of collapse load. One is static theorem, one is kinematic theorem. Okay. Static theorem and kinematic theorem. So we will discuss one by one today. Static theorem, kinematic theorem. So what static theorem says? For given structural system and load arrangement, for given structural system like the cross section of beam, length of beam, that should be known. For given structural system means end condition, span, number of span, that is nothing but the structural system, and load arrangement, and what are the loads are acting over that system. Structural systems and load arrangement means load acting on the system. If there exists any bend moment distribution which is statically admissible and safe. Okay. So for given structural system and load, if that system exists any bend moment distribution which is statically admissible and safe, that should be statically admissible and safe, or when you have to use this static theorem, or the shape of bend moment diagram should be easily known. For given set of load, the value of load W should be less than or equal to WC. So when you use static theorem, the shape of bending moment diagram should be easily known. When you can use static theorem for the calculation of collapse load WC, so WC is nothing but collapse load, when the shape of bending moment diagram should be easily known, and that should be statically admissible and safe. When you use static theorem, the shape of bending moment diagram should be easily known. If you don't know the bending moment diagram, you cannot use static theorem for the calculation of collapse load. We cannot use the static theorem if you don't know the bending moment diagram, which is statically admissible and safe. We cannot use static theorem. So that's why it is given as, for given set of structural system and load arrangement, if there exists any bending moment distribution which is statically admissible or safe, and the shape of bending moment diagram should be easily known, then and then only we can use static theorem. Okay. Then what kinematic theorem says? For a given structural system and load arrangement. Again, here also we should have the structural system, whether it is a beam section, portal frame, the span, whether it is cantilever, overhang, everything that comes under structural system, and load arrangement. Value of load corresponding to any assumed mechanism will be either equal to or greater than WC. So here in kinematic theorem we have to assume a mechanism. Here we don't want to have the bending moment distribution or the bending moment diagram. Here we can assume a mechanism. How mechanism means, again, how the structure will bear the load or try to collapse. Where the structure will collapse, that mechanism you have to assume. Based on any assumed mechanism will be either equal to or greater than WC. Okay. What is assumed mechanism then? Assumed mechanism is the number of hinges assumed which can convert the structure into mechanism. So we have to assume a mechanism by assuming the number of hinges developed, number of plastic hinges developed in the section to convert the structure into mechanism. Once if you form a mechanism, we can easily find out the collapsible load or the WC. Okay. So we will discuss about the steps, how to follow the steps in both the methods. So in the static theorem, the steps are: first, draw a bending moment diagram for external load. So first step you have to find out the bending moment diagram, because without bending moment diagram we cannot find out the WC. So first of all, draw a bending moment diagram for external load. Then choose the maximum ordinate of bending moment. Why you have to choose maximum ordinate? Because where the bending moment will be maximum, there the collapse will occur. So we have to choose the maximum ordinate of bending moment. Check whether it is sufficient to form mechanism. Then we have to check whether that ordinate is sufficient to form or that structure, the system is sufficient to form a mechanism. Then find WC. Okay. Then after that, assume a mechanism. You have to assume a mechanism in the kinematic theorem. You have to assume a mechanism. Apply principle of virtual work to compute the collapse load. So here, by assuming mechanism, we have to apply a principle of virtual work. Virtual work, that is, principle of virtual work is nothing but internal work done should be equal to external work done. So what is principle of virtual work? What it says? It is nothing but internal work done should be equal to external work done. So by applying that theorem or the principle of virtual work to compute we can very easily find out the collapse load. So these are the steps you have to follow to determine the collapse load. Understood? So one thing is here, now hinges, we have got one more word, that is called as plastic hinge. So what is plastic hinge? Okay, we are going to discuss what is plastic hinge. Okay. So here, so what is plastic hinge? We are going to discuss. So we have a load again, a structural system with a load, external load, a structural system with given load, a beam with a given load. So what will happen? Again, with respect to the stress distribution in the beam, okay, when the load goes on increases over the section, the body will offer resistance, internal resistance. Again, if you go on increasing load, the body will start deflecting. Or it will develop the stresses. So at the first stage, at the first stage for a given cross section. For a given cross section, at the first level, when you apply load and when you release, the body will tends to go back to original position. So at the first stage, it will be, the behavior will be in elastic stage. So we can see the stretch strain. Here we can see the tension T, and here it will be compression. So that is called as elastic. Again, if you go on increasing load, this I have discussed in the first session of plastic analysis also. What is happening here? First it was in elastic stage. Again, when you gradually increase the load, when I increase the load again, the some part of the beam start yielding. It will form a cup like this. Try to yield like this. Try to. If you see the cross section here, and if you see the cross section, it is start yielding here. Again, the load, if it is increased, so this is called as elastoplastic. This is called as elastoplastic. Again, when the load increase gradually over this section, again the behavior will transform. It was in this zone when it was elastoplastic. So what will happen? It will become like this. The section will yield and it will become like this. It has first, when the load was applied and when the load released, it will used to come back to original position. So that's why it is elastic. When the load still gradually increase, it will start yielding. So neither it was fully elastic or fully plastic in this second zone. So this is for second, this is for third, okay, and this is for first. So this is first, second and third I will draw now. So in first stage, the body in totally elastic zone. Second stage, the load were increased gradually, the body will try to start yielding at the maximum bending moment, yield at the level of maximum bending moment. But the body is neither fully elastic or fully plastic. The bottom part here has reached plastic, but this is still in elastic. This part is still in elastic, this part we can say. So this part still in elastic zone. But still, when the load increases, so it will transform its behavior from elastoplastic to fully plastic. So the total cross section at the maximum bending moment will yield. So that times it is called as fully plastic. So the member changes its behavior from elastic to elastoplastic. Again, the load increased, member transformed its behavior from elastoplastic to fully plastic. So during that time what will happen? So this axis will become as equal area axis. When the section gets fully plastified, the neutral axis will transform to equal area axis. The neutral axis will transform to, or it will overlap over equal area axis. So what is seen? The plastic hinge is a section at which all fibers completely yielded. The plastic hinge, it's a level at which all fibers have completely yielded and plastified. All fibers have completely yielded and plastified. The fibers on one side of equal area axis, are in compression. So these fibers, these are the fibers under compression and these fibers will be under tension, which will try to expand, try to contract. यहाँ पे होगा contract होगा, यहाँ पे expand होगा. The section after that, the section will act like a hinge. The section will act like a hinge. So it will not take any movement further when it fully plastified. So what is hinge? It will not take any movement. So when it will reach to the fully plastic stage, it will not take any movement. यहाँ पे वो movement लेता था, यहाँ पे लेता था, but when it reaches here, it will not take any movement. So it will act as a hinge, and that hinge is known as plastic hinge, and that hinge is known as plastic hinge. When the section get fully plastified and it will act as a hinge, and that hinge is called as plastic hinge. That hinge is called as plastic hinge. Understood? So next is, we have just discussed about plastic hinge, and where will they form? Where will they form? Where the plastic hinge will form. Okay, the plastic hinge will form in the structure, but where? That. Then how many numbers? 1 number, 2 numbers, how many numbers they will form? So that we are going to discuss. So where they will form? So first section where bending moment is maximum. The first where they will occur, where the bending moment is maximum. Okay. So where the first is, suppose a beam simply supported with UDL or a point load. So bending moment will be like this. So first plastic hinge कहाँ पे form आगा? यहाँ पे. The first plastic hinge where we have the maximum bending moment. That is the first. Okay, the first. Then next point of zero shear force, where the point of under concentrated load. First is where the location of maximum bending moment, there the plastic hinge will form under the concentrated load. So where we have, so again it is the same, because the bending moment is, and the location of bending moment and the concentrated load is same, so that's why we will get the plastic hinge here only. Then point of zero shear force, where we will get the point of zero shear force, there we can have the plastic hinge. Then fourth one is at fixed supports, where we will have fixed support, there the plastic hinge will form. Then section where moment of inertia changes. Section where moment of inertia changes, मतलब अभी यहाँ पे देखो, we have a section like this, okay. Here it is mi and here it is 2i, I and 2i. तो यहाँ पे क्या हुआ, location change हुआ, so here the plastic hinge will form. First of all, at maximum bending moment, at concentrated load, then at fixed supports. कहाँ पे fixed support होगा, वहाँ पे plastic hinge form होगा. Then where the shear force is zero, so here also the plastic hinge will form. Then fourth one is, the last one is where the moment of inertia changes, there the plastic hinge will form. समझ में आपको? These are the locations where the plastic hinge will form. The next is how many numbers? So the structure is statically indeterminate to degree n, to the degree of n. Then n plus 1 hinges are required to form a mechanism. Suppose there is a beam which is statically indeterminate with the degree of n. Then n plus 1 hinges are required to convert that structure into mechanism. So I will give a small example here. Example, how many numbers of plastic hinges will form? Okay, the structure or member is statically indeterminate. Which structure is statically indeterminate to degree of n? Then the n plus 1 hinges required to form a mechanism. Okay, तो यहाँ पे देखो, we have one beam which is fixed at one support and roller or the hinge at another support, and which is subjected to a concentrated load. तो यहाँ पे देखो, अभी इसका स्टैटिक whether it is statically determinate or indeterminate, we have to find out that. So the reaction is, total reactions are 2 plus 1. First of all, see, for fixed supports we have 3 reactions, one horizontal, one vertical and one moment. So horizontal reaction we are ignoring here because there is no horizontal load. So generally I think you have studied in structural analysis, we generally ignore the horizontal reaction. So we consider only 2, that is at fixed supports one is vertical reaction, one is movement, and at roller supports we have vertical reaction, only vertical reaction. Okay, so कितने reactions हुए? R is equal to 2 plus 1, that is equal to 3. Then the number of equations of equilibrium are 3 because the total are 3 plus minus 1 for horizontal, we are not considering horizontal, so therefore it is 2. So R is equal to 2 plus 1, 3. Number of equations of equilibrium is equal to 2. So N is equal to R minus 2. So the total reactions minus equations of equilibrium 1. So degree कितना हुआ हमारा N. So hence the plastic hinges required to convert the structure into mechanism H. The plastic hinges H is equal to N plus 1. So we required 2 plastic hinges to convert this structure into mechanism. We require 2 plastic hinges. We require 2 plastic hinges to convert this structure into mechanism. Understood? So 2 numbers of plastic hinges are required because what they were given, degree N, then N plus 1 hinges are required. N plus 1 hinges are required. Okay. So now again we'll come back to this. Where will they form? Where will they form? तो यहाँ पे different options हैं. एक कहाँ पे होगा? Maximum bending, concentrated load, zero shear force, fixed support, and where the moment of inertia changes. So we'll see here. First plastic hinge, where they will form? First is where the maximum bending moment is there. तो यहाँ पे maximum bending moment कहाँ पे है? So first of all, the first plastic hinge will form here. So this is clear. Section where maximum bending moment. So here we have a maximum bending moment. The first plastic hinge will form here. So I'll write 1. The first plastic hinge will form. Then under concentrated load. So the location of concentrated load and the maximum bending moment is same. So we cannot repeat again. So here 1. So we have 2 options is over. 3 for zero shear force. So where the bending moment maximum, so there will be shear force will be 0. So again no need to give the same plastic hinge at same location. Then next fixed support. Fixed support. One more option we can check, that is section where moment of inertia changes. यहाँ पे कुछ change हो रहा है क्या? नहीं. So that will not be applicable. But this is applicable where we can form a plastic hinge where the fixed support is there. So 2. तो कितने हुए plastic hinge? 1, 2, 2. So how many number of plastic hinges are required? 1 plus 1, 2, 2. So because of forming the plastic hinges at 1 and at 2, this structure or the member will convert into mechanism. So we'll see one more example, I think. Okay, here you can see one more example. So same here, but both side we have one side hinge and one is roller. तो यहाँ पे reactions कितने होंगे? One reaction, one reaction. So R is 2, correct? R is equal to 2. Understood? And the equations of equilibrium N is equal to 2. So therefore, and we require the plastic hinges N plus 1. What rule says? The plastic hinge required to convert the structure into mechanism, we required N plus 1. तो क्या होगा यहाँ पे? So N minus R is equal to 0 because 2 minus 2 is 0. तो कितने hinges चाहिए हमारे यहाँ पे? So H should be equal to 0 because N is 0. So N, sorry, this is not N. Number of equations of equilibrium, see, are 2. So N minus R, sorry, 2 minus, sorry, so R minus the equations of equilibrium are 0. Okay, you can see here the reactions are 2 and the equations of equilibrium are also 2. So R minus 2 is equal to 0. So H, so that is N is equal to, sorry, N is equal to R minus 2. N is equal to R minus 2. So N कितना मिला हमको? 0. So H should be equal to n plus 1. So how many plastic hinges are required? We required one plastic hinge to convert the structure into mechanism. Okay. So I'll repeat once again. यहाँ पे अगर आपको कुछ confusion हुआ है तो the reactions are equal to 2 and the equations of equilibrium are also 2. So therefore n is equal to r minus 2, so 0. So therefore we required the plastic hinges H, that is n plus 1. So n is 0, n plus 1. So required one plastic hinge. We required one plastic hinge to convert the structure into mechanism. Now we got the number, that is 1. Abhi where they will form? Where will they form? So first at the maximum bending moment or at the concentrated load. फिक्स सपोर्ट, यहाँ पे फिक्स सपोर्ट नहीं है, मोमेंट ऑफ इनर्शिया चेंज हो रहा है, नहीं हो रहा है. सो वेयर वी हैव द कॉन्सेंट्रेटेड लोड और मैक्सिमम बेंडिंग मोमेंट. सो विल ड्रॉ द बेंडिंग मोमेंट डायग्राम हियर. So this is the bedding moment diagram. Okay, so one plastic hinge. So I can locate here. So this is a plastic hinge. We required only one plastic hinge. We required only one plastic hinge to convert the structure into mechanism. So we required one. So we have provided, which is under concentrated load and under maximum bending moment. So this is regarding how to convert the structure into collapsible mechanism. So same way. So these methods we are going to follow. Okay, these two methods we are going to follow to determine the collapse load. Okay, and once if you know the collapse load, we can restrict the load acting over the section. Okay, thank you.